In number theory, the prime number theorem describes the asymptotic distribution of the prime numbers. The prime number theorem gives a general description of how the primes are distributed amongst the positive integers. It formalizes the intuitive idea that primes become less common as they become larger. Informally speaking, the prime number theorem states that if a random integer is selected in the range of 0 to some large integer n, the probability that the selected integer is prime is about 1/ln, n, where ln, n, is the natural logarithm of n. Consequently, a random integer with at most 2 n digits is about half as likely to be prime as a random integer with at most n digits. For example, among the positive integers of at most 1000 digits, about 1 in 2300 is prime, whereas among positive integers of at most 2000 digits, about 1 in 4600 is prime. In other words, the average gap between consecutive prime numbers among the first n integers is roughly ln, n. Statement. Let x be the prime counting function that gives the number of primes less than or equal to x, for any real number x. For example, I10 equals A4 because there are 4 prime numbers less than or equal to 10. The prime number theorem then states that x/ln, x, is a good approximation to I in the sense that the limit of the quotient of the two functions x, and x/ln, x, as x approaches infinity is 1. Known as the asymptotic law of distribution of prime numbers. Using asymptotic notation, this result can be restated as: this notation does not say anything about the limit of the difference of the two functions as x approaches infinity. Instead, the theorem states that x/ln, x, approximates x, in the sense that the relative error of this approximation approaches 0 as x approaches infinity. The prime number theorem is equivalent to the statement that the nth prime number Pn satisfies the asymptotic notation, meaning again that the relative error of this approximation approaches 0 as n approaches infinity. For example, the 200 to 1015th prime number is 8512677386048191063, ANDLN, 200 to 1015, rounds to 79674187522917443888, a relative error of about 6.8%. The prime number theorem is also equivalent to, and. History of the asymptotic law of distribution of prime numbers and its proof. Based on the tables by Anton Felkel and George Vega, Adrian Marie Legendre conjectured in 1797 or 1798 that a is approximated by the function a/ln, a plus a b, where a and b are unspecified constants. In the second edition of his book on number theory, he then made a more precise conjecture, with all equals a1 and bi equals a1.08366. Carl Friedrich Gauss considered the same question at age 15 or 16 in Sjar 1792 oder 1793, according to his own recollection in 1849. In 1838 Peter Gustav Lejeune Dirichlet came up with his own approximating function, the logarithmic integral Li, x. Both Legende's and Dirichlet's formulas imply the same conjectured asymptotic equivalence of x, and za/ln, x, stated above, although it turned out that Dirichlet's approximation is considerably better if one considers the differences instead of quotients. In two papers from 1848 and 1850, the Russian mathematician Pafnutilrovich Chebyshev attempted to prove the asymptotic law of distribution of prime numbers. His work is notable for the use of the zeta function I paragraph, s, predating Riemann's celebrated memoir of 1859, and he succeeded in proving a slightly weaker form of the asymptotic law, namely, that if the limit of x, ln, x as x goes to infinity exists at all, then it is necessarily equal to 1. He was able to prove unconditionally that this ratio is bounded above and below by two explicitly given constants near to 1 for all x. Although Chebyshev's paper did not prove the prime number theorem, his estimates for x was strong enough for him to prove Bertrand's postulate that there exists a prime number between n and 2n for any integer now a permil beta 2. An important paper concerning the distribution of prime numbers was Riemann's 1859 memoir on the number of primes less than a given magnitude, the only paper he ever wrote on the subject. Riemann introduced new ideas into the subject, the chief of them being that the distribution of prime numbers is intimately connected with the zeros of the analytically extended Riemann zeta function of a complex variable. In particular, it is in this paper of Riemann that the idea to apply methods of complex analysis to the study of the real function I(x) originates. Extending the ideas of Riemann, two proofs of the asymptotic law of the distribution of prime numbers were obtained independently by Jacques Hadamard and Charles-Jean de Laval, copyright E. Poussin, and appeared in the same year. Both proofs used methods from complex analysis, establishing as a main step of the proof that the Riemann zeta function I(s) is non-zero for all complex values of the variable s that have the form za equals a1 a plus a with tau a0. During the 20th century, the theorem of Hadamard and de Laval, copyright E. Poussin, also became known as the prime number theorem. Several different proofs of it were found, including the elementary proofs of Eitel Selberg and Paul Erdős. While the original proofs of Hadamard and de Laval, copyright E. Poussin, are long and elaborate, and later proofs have introduced various simplifications through the use of Tauberian theorems but remain difficult to digest, a short proof was discovered in 1980 by American mathematician Donald J. Newman. Newman's proof is arguably the simplest known proof of the theorem, although it is non-elementary in the sense that it uses Cauchy's integral theorem from complex analysis. Proof methodology. In a lecture on prime numbers for a general audience, Fields medalist Terence Tao described one approach to proving the prime number theorem in poetic terms, listening to the music of the primes. We start with a sound wave that is noisy at the prime numbers and silent at other numbers. This is the von Mangolt function. Then we analyze its notes or frequencies by subjecting it to a process akin to Fourier transform. This is the Mellin transform. The next and most difficult step is to prove that certain notes cannot occur in this music. This exclusion of certain notes leads to the statement of the prime number theorem. According to Tao, this proof yields much deeper insights into the distribution of the primes than the elementary proofs. Proof sketch. Here is a sketch of the proof referred to in Tao's lecture mentioned above. Like most proofs of the PNT, it starts out by reformulating the problem in terms of a less intuitive, but better behaved, prime counting function. The idea is to count the primes with weights to arrive at a function with smoother asymptotic behavior. The most common such generalized counting function is the Chebyshev function, defined by. This is sometimes written as, where is the von Mangolt function, namely. It is now relatively easy to check that the PNT is equivalent to the claim that. Indeed, this follows from the easy estimates. And for any. The next step is to find a useful representation for. Let be the Riemann zeta function. It can be shown that is related to the von Mangolt function, and hence to, via the relation. A delicate analysis of this equation and related properties of the zeta function, using the Mellin transform and Perron's formula, shows that for non-integer x the equation holds, where the sum is over all zeros of the zeta function. This striking formula is one of the so-called explicit formulas of number theory, and is already suggestive of the result we wish to prove, since the term x appears on the right-hand side, followed by lower-order asymptotic terms. The next step in the proof involves a study of the zeros of the zeta function. The trivial zeros a2, a4, a6, a8 can be handled separately, which vanishes for a large x. The non-trivial zeros, namely those on the critical strip, can potentially be of an asymptotic order comparable to the main term x if, so we need to show that all zeros have real parts strictly less than 1. To do this, we take for granted that is meromorphic in the half-plane, and is analytic there except for a simple pole at, and that there is a product formula for this product formula follows from the existence of unique prime factorization of integers, and shows that is never zero in this region, so that its logarithm is defined there and right. Then. Now observe the identity so that. For all. Suppose now that. Certainly is not zero, since has a simple pole at. Suppose that and let tend to from above. Since has a simple polet and stays analytic, the left-hand side in the previous inequality tends to a contradiction. Finally, we can conclude that the PNT is morally true. To rigorously complete the proof there are still serious technicalities to overcome, due to the fact that the summation over zeta zeros in the explicit formula for does not converge absolutely but only conditionally and in a principal value sense. There are several ways around this problem, but many of them require rather delicate complex analytic estimates that are beyond the scope of this article. Edwards's book provides the details. Another method is to use Eichhorer's Tauberian theorem, though this theorem is itself quite hard to prove. D. J. Newman observed that the full strength of Eichhorer's theorem is not needed for the prime number theorem, and one can get away with a special case that is much easier to prove. Prime counting function in terms of the logarithmic integral, in a handwritten note on a reprint of his 1838 paper Sur l'usage des arts copyright Rise Infinis dans l'art copyright des nombres, which he mailed to Carl Friedrich Gauss, Peter Gustav Lejeune Dirichlet conjectured that an even better approximation to I euro, x, is given by the offset logarithmic integral function Li, x, defined by. Indeed, this integral is strongly suggestive of the notion that the density of primes around T should be 1/ln T. This function is related to the logarithm by the asymptotic expansion. So, the prime number theorem can also be written as I euro, x, Li, x. In fact, it follows from the proof of Hadamard and de la Valle copyright E. Poussin that for some positive constant where O, a euro is the big O notation. This has been improved too. Because of the connection between the Riemann zeta function and I euro, x, the Riemann hypothesis has considerable importance in number theory. If established, it would yield a far better estimate of the error involved in the prime number theorem than is available today. More specifically, Helge von Koch showed in 1901 that, if and only if the Riemann hypothesis is true, the error term in the above relation can be improved to. The constant involved in the big O notation was estimated in 1976 by Lowell Schoenfeld, assuming the Riemann hypothesis. For all xa per mil 2,657 yen. He also derived a similar bound for the Chebyshev prime counting function I. For all xa per mil 73.2 yen. This latter bound has been shown to express a variance to mean power law, 1 per Fahrenheit noise, and to also correspond to the Tweedy compound Poisson distribution. Parenthetically, the Tweedy distributions represent a family of scale invariant distributions that serve as foci of convergence for a generalization of the central limit theorem. The logarithmic integral Li, x, is larger than I euro, x, for small values of x. This is because it is counting not primes, but prime powers, where a power Pn of a prime P is counted as 1/n of a prime. This suggests that Li, x, should usually be larger than I euro, x, by roughly Li, x 12, and in particular should usually be larger than I euro, x. However, in 1914, J. E. Littlewood proved that this is not always the case. The first value of x where I euro, x, exceeds Li, x, is probably around x equals 10,316. See the article on Skew's number for more details. Elementary proofs. In the first half of the 20th century, some mathematicians believed that there exists a hierarchy of proof methods in mathematics depending on what sorts of numbers a proof requires, and that the prime number theorem is a deep theorem by virtue of requiring complex analysis. This belief was somewhat shaken by a proof of the PNT based on Wiener's Tauberian theorem, though this could be set aside if Wiener's theorem were deemed to have a depth equivalent to that of complex variable methods. There is no rigorous and widely accepted definition of the notion of elementary proof in number theory. One definition is a proof that can be carried out in first-order Peano arithmetic. There are number theoretic statements provable using second-order but not first-order methods, but such theorems are rare to date. In March 1948, Eitel Selberg established, by elementary means, the asymptotic formula. Where? For primes. By July of that year, Selberg and Paul Erdős had each obtained elementary proofs of the PNT, both using Selberg's asymptotic formula as a starting point. These proofs effectively laid to rest the notion that the PNT was deep, and showed that technically elementary methods were more powerful than had been believed to be the case. In 1994, Charalambos Kornaros and Kostas Dimitrakopoulos proved the PNT using only a formal system far weaker than Peano arithmetic. On the history of the elementary proofs of the PNT, including the Adesa-Selberg priority dispute, see Dorian Goldfeld. Computer verifications. In 2005, Avogadro et al. Employed the Isabelle theorem prover to devise a computer-verified variant of the Adesa-Selberg proof of the PNT. This was the first machine-verified proof of the PNT. Avogadro chose to formalize the Adesa-Selberg proof rather than an analytic one because while Isabelle's library at the time could implement the notions of limit, derivative, and transcendental function, it had almost no theory of integration to speak of. In 2009, John Harrison employed HOL-like to formalize a proof employing complex analysis. By developing the necessary analytic machinery, including the Cauchy integral formula, Harrison was able to formalize a direct, modern and elegant proof instead of the more involved unregistered trademark Erda paragraphs Selberg argument prime number theorem for arithmetic progressions. Let denote the number of primes in the arithmetic progression a plus n, a plus 2n, a plus 3n, less than x. Lejeune Dirichlet and Legendre conjectured, and Valla copyright E. Poussin proved, that, if a and n are k', then where is the Euler's totient function. In other words, the primes are distributed evenly among the residue classes, a, modulo n with GCD, n, equals 1. This can be proved using similar methods used by Newman for his proof of the prime number theorem. The Siegele-Wolfice theorem gives a good estimate for the distribution of primes in residue classes. Prime number race, although we have in particular. Empirically the primes congruent to 3 are more numerous and are nearly always ahead in this prime number race. The first reversal occurs at x equals 26,861. However, Littlewood showed in 1914 that there are infinitely many sign changes for the function. So the lead in the race switches back and forth infinitely many times. The phenomenon that €4, 3, x, is ahead most of the time is called Chebyshev's bias. The prime number race generalizes to other moduli and is the subject of much research. Par Eltura N asked whether it is always the case that I x, a, c, and I x, b, c, change places when a and b are k' to c. Granville and Martin give a thorough exposition and survey. Bounds on the prime counting function. The prime number theorem is an asymptotic result. It gives an ineffective bound on I x, as a direct consequence of the definition of the limit. For all I micron 0, there is an S such that for all x, S. However, better bounds on I x are known, for instance Pierre-Diozat's. The first inequality holds for all XA per mil 599 yen and the second one for XA per mil 355,991 yen. A weaker but sometimes useful bound for XA per mil 55 yen is. In Diozat's thesis there are stronger versions of this type of inequality that are valid for larger x. The proof by de la Valle copyright E. Poussin implies the following. For every I micron 0, there is an S such that for all x, S. Approximations for the nth prime number, as a consequence of the prime number theorem, one gets an asymptotic expression for the nth prime number, denoted by Pn. A better approximation is. Again considering the 21015 prime number 8512677386048191063, this gives an estimate of 8512681315554715386. The first 5 digits match and relative error is about 0.00005%. Rosser's theorem states that Pn is larger than n An. This can be improved by the following pair of bounds. Table of I x, x/ln x, and li, x. The table compares exact values of I x to the two approximations za/ln ax and li, x. The last column, za/ai x, is the average prime gap below x. The value for I 1024 was originally computed assuming the Riemann hypothesis. It has since been verified unconditionally. Analog for irreducible polynomials over a finite field, there is an analog of the prime number theorem that describes the distribution of irreducible polynomials over a finite field. The form it takes is strikingly similar to the case of the classical prime number theorem. To state it precisely, let F equals GF, Q, be the finite field with Q elements, for some fixed Q, and let Nn be the number of monic irreducible polynomials over F whose degree is equal to n. That is, we are looking at polynomials with coefficients chosen from F, which cannot be written as products of polynomials of smaller degree. In this setting, these polynomials play the role of the prime numbers, since all other monic polynomials are built up of products of them. One can then prove that if we make the substitution x equals Qn, then the right-hand side is just. Which makes the analogy clearer. Since there are precisely Qn monic polynomials of degree n, this can be rephrased as follows: if a monic polynomial of degree n is selected randomly, then the probability of it being irreducible is about a 1/n. One can even prove an analog of the Riemann hypothesis, namely that the proofs of these statements are far simpler than in the classical case. It involves a short combinatorial argument, summarized as follows. Every element of the degree n extension of F is a root of some irreducible polynomial whose degree d divides n. By counting these roots in two different ways one establishes that where the sum is over all divisors d of n. Ma paragraph bias inversion then yields where I1/4, k, is the Ma paragraph bias function. The main term occurs for d equals n, and it is not difficult to bound the remaining terms. The Riemann hypothesis statement depends on the fact that the largest proper divisor of n can be no larger than n/2. See also, Abstract Analytic Number Theory for information about generalizations of the theorem. Landau prime ideal theorem for a generalization to prime ideals in algebraic number fields. Riemann hypothesis, notes. References: Hardy, G.H. and Littlewood, J.E. Contributions to the theory of the Riemann zeta function and the theory of the distribution of primes. Acta Mathematica 41, 119 a €196 doi, 10.1007/BF02422942 Granville, Andrew. Harold Kramer copywriter in the distribution of prime numbers. Scandinavian Actuarial Journal 1, 12 a €28 doi, 10.1080/0346123.1995.10413946 External links, Haswinkel, Michiel, ed., Distribution of Prime Numbers, Encyclopedia of Mathematics, Springer, ISBN A978-1-55608-010-4, Table of Primes by Anton Felkel. Short video visualizing the prime number theorem. Prime formulas and prime number theorem at MathWorld. Prime number theorem at planetmath.org. How many primes are there? And the gaps between primes by Chris Caldwell, University of Tennessee at Martin. Tables of prime counting functions by Toma S. Oliveira e Silva.